Good afternoon, all. Myself, Dr. Rakshit Bihar, Assistant Professor, Department of Mathematics, VVCE, Mysuru. So, I welcome all of you for this online training and mock exam on GATE 2021. So, today I'll be just discussing about the topics in GATE 2021. More specifically, we will be discussing about the engineering mathematics with respect to GATE 2021. So, firstly, let me just list out the syllabus that's included in your GATE 2021. So, under engineering mathematics. So, the syllabi are as follows. The very first topic is linear algebra. So, under this, we have vector spaces, basis, linear dependence, independence, matrix algebra, eigenvalues, rank, and solution of linear equations and its existence and uniqueness. And second topic is the calculus. So under this we have the mean value theorems, maxima, minima, surface integrals, Taylor series, partial derivatives. All these things comes under this topic calculus. And nextly we have this differential equation. So where you must know how to solve a first order differential equation and the solutions of higher order differential equations, Cauchy's and Euler's equations, and also certain methods to solve the differential equation of higher order, specifically the method of variation of parameter, complementary functions, and particular integrals, and the initial and boundary value problems. And also three more topics. One is vector calculus. So the other one is complex analysis, where you must know what is meant by the Cauchy's integral theorem, Cauchy's integral formula, sequential series, Taylor's and Lorentz series, residue theorems. And the last topic is the probability theory and statistics. So this is the syllabus for the GATE 2021 under the section Engineering Mathematics. So we have only 6 topics: linear algebra, calculus, differential equation, vector analysis, complex analysis, probability, and statistics. So today I'll be dealing with the topic linear algebra and the differential equations. So within this the time 2 hours did not just cover the entire range. So I'll just picking some topics in this syllabus, and we'll discuss some questions that has appeared in your previous GATE exam. Okay. So let me just start with the topic linear algebra. So from linear algebra, I need to just first talk about what's meant by rank of a matrix. So this tool indeed helps us to crack many of the problems, right? So if you know how to compute a rank, then you can just solve plenty of problems in this linear algebra. Okay. So firstly, let me just tell you what's meant by a rank of a matrix. So there are plenty of definitions, equivalent definitions to rank. So before just defining what's meant by rank of a matrix, I need to tell you something what's called as an echelon matrices. So what is meant by an echelon matrices? This matrix, it's a tool, it's a nice form, so with which one can analyze the given matrix. That means one can analyze what's its rank. Rank is equivalent to number of linearly independent rows or columns. So before stating the definition of rank of a matrix explicitly, let me just tell you what meant by an echelon matrix. So a matrix A is said to be an echelon matrix. A matrix A is said to be an echelon matrix, or we say that it's in the form of echelon form. It's in the echelon form if it satisfies 2 conditions. So the condition number 1 is that so all 0 rows in that matrix, if any, right? So all 0 rows in that matrix say if any. That means if not, fine. If any, then it must be at the bottom of the matrix. Then it must be at the bottom of the matrix. The second condition is that each leading non-zero entry. So what's meant by this leading non-zero entry in a row? So leading non-zero entry in a row stands for the first non-zero entry in a row. So if each leading non-zero entry in a row is towards the right of the first non-zero entry in the preceding row, then we are going to say that A is an echelon matrix. So you will understand better. So if I just consider the following example. So the point number one is that if you want going to say that it's in echelon form or it's an echelon matrix, the point number one is that the condition number one is that all zeros, if any, are at the bottom of the matrix, and each leading non-zero entry in a row is to the right of the first non-zero entry in the preceding row. So this leading non-zero entry is well known by the word pivot element. It's well known by the word pivot element. So let me just give two examples. So one which is in echelon form, the other which is not in echelon form. So if you consider this matrix A, just observe that if you want to say this is an echelon matrix, then it must satisfy two conditions, as I told earlier. Okay. So and you can see it on the screen also. It must satisfy the condition 1 and 2. So if you look at this matrix A, you first observe that all these 0 rows, it has got 1 0 rows, okay, but it's at the bottom. Okay, fine. So it satisfies the first condition. And look into the leading non-zero entry in each of the row, it must be towards the right of the previous first non-zero entry in the preceding row, in the previous row. So if I just consider this second row, what's its first non-zero entry? Its first non-zero entry is nothing but A, 2, 3, that is 1. So and this non-zero entry in the second row is towards the right of the first non-zero entry in the first row. Right? Okay, fine. So likewise, you need to check it for each row whether the leading non-zero entry in a row is to the right of the leading non-zero entry in the preceding row. So here we can check. So if you consider the leading non-zero entry in the third row, so it is 3. So and it is towards the right of that of the leading non-zero entry in the preceding row. Right? It is towards the right. Okay, fine. So therefore it satisfies this matrix A, it satisfies both the conditions 1 and 2, and hence you can say that it's an echelon matrix, or in other words, they say that it's an echelon form. Okay? So let me just consider one more example where we can conclude that this is not an echelon form. So for example, if you consider the matrix A, so you can see that it satisfies the first conditions. That means all zeros, if any, are at the bottom. Yeah, all zeros are at the bottom. Fine. And now we just check whether it satisfies the condition 2. Okay. So for this, if you have a look into the second row, its first non-zero entry is 1. Its first non-zero entry is 1, but this is not towards the left, towards the right of the leading non-zero entry in the preceding row. It is towards the left of the leading non-zero entry in the previous row, right? So previous row, that is, if you consider the first row, the leading non-zero entry is at the third position, whereas in the second row, the leading non-zero entry is at the second position. So this is not allowed. So therefore, we can say that this matrix A is not an echelon matrix, or it is not in the echelon form. Okay. So this information, this definition is very useful because every matrix you can just put it in the form of echelon form, and therefore you can just find out what is the type. So I hope you got the definition of an echelon matrix, right? So now let me just tell you what is meant by a row equivalence. Suppose here we just consider a matrix A. Then we say that A is row equivalent to a matrix B. Then we say that A is said to be row equivalent to a matrix B if B can be obtained from the matrix A. If you can derive a matrix B from the matrix A by a sequence of elementary row operation. By a sequence of elementary row operations. So that means if from the matrix A, if you are able to obtain another matrix by a sequence of row operations, what are the row operations? Elementary row operations. They are nothing but row replacement, interchanging, multiplying a row by a scalar, addition of rows. All these are basic eliminatory operations. So if you obtain another matrix B from A by this sequence of eliminatory row operations, then we say that A and B are row equivalent. So this is a nice relationship. Okay. So this is the definition of row equivalence. Suppose you got B. Suppose the so obtained B is in an echelon form. Suppose the so obtained B is an echelon matrix. Then we say that B is an echelon form of A. Okay. So first you need to know what's meant by row equivalence. So row equivalence means from the given matrix A, you will be just performing a sequence of eliminatory operations to obtain a matrix B. So if this is the case, then we say that A and B are row equivalents, right? And so obtain matrix B, if it's in the form of, if it's an echelon matrix, then we say that B is an echelon form of A. So one point you need to remember that the echelon form is not unique. Given any matrix, you can find out its echelon form, but it's not unique. Okay? There are other equivalent definitions. So row canonical form, all those things are or reduced echelon matrix. So, but this information is enough to solve problems. Okay. So one point you need to know what's meant by an echelon matrix. The other thing you need to know, that every matrix you can just find out what is its echelon form by just performing a sequence of elementary row operations. The third point now, the question is that how to determine this echelon form. Okay, so before that, let me just give the definition of the rank of a matrix. So rank of a matrix, you can just define it in by many number of ways. All the definitions will be one and the equivalent. So, but here I just consider this definition. So I just consider rank of a matrix A to be the number of non-zero rows in its echelon form. So rank of a matrix A, we used to denote it by this rank of A. It is equal to the number of non-zero rows in echelon form. So you can have many definitions for rank. So actually, a very powerful definition is that this rank simply stands for the number of linearly independent rows. So that's what you are counting here. Number of non-zero rows in an echelon form gives you the number of linearly independent rows in the matrix A. Okay, so or linearly independent columns, both they are one and the same. Or you can also define rank as the number of non-zero eigenvalues. One might define rank of matrix as the number of non-zero eigenvalues. So that's also fine. And also you can define the rank as the maximum non-singular submatrix of a matrix A. The maximum order of a non-singular submatrix of the matrix A, it is called as a rank. So there are plenty of definitions. All these they are one and the same. So, but you need to know what's meant by a rank. Actually, it stands for the number of linearly independent rows. So that is equivalent to saying that it is equal to the number of non-zero rows in its echelon form. So now the question is how to get this echelon form of a given matrix, how to find out its echelon form, how to find out the echelon form of a given matrix. So for this, you all know what's meant by this Gaussian elimination process, right? So by solving the linear system of equations, so you might have come across this method, the Gaussian elimination method, right, or Gauss-Jordan elimination method. So here, the word Gauss elimination, indeed, it said you are just getting its echelon form and then solving the equation, by back substitution, right? So here, with the help of this Gauss elimination, you can find out what is the echelon form of the given matrix. You can find out its echelon form and hence the rank of the given matrix. So for example, to illustrate this Gaussian elimination, I just consider the matrix here. So I am just to find out its echelon form. So note that echelon form is not unique. So it changes, it depends upon how you approach. Okay. So if I consider this matrix A, So I need to find out its echelon form. So I need to recall what's meant by this Gaussian elimination is. So in this echelon form, you can see that if you want to get its echelon form, the very first step is that you just consider the pivot element in the first row. So here the pivot element. Pivot element means the first non-zero entry. So the first non-zero entry in the first row here it is 1. Right? You just consider this first row, and using this first row, try to eliminate the entries 2 and 3. Try to eliminate the entries in the first column. The second entry, the third entry in the first column, make it as 0 using the first row. So how do I make it this as 0? By using row operations. So I want, in place of 2, I want to get it as 0. So using row operations, you can do it by just multiplying the first row by -2 and summing it to the second row. And also you can make this the number 3 as 0 by just multiplying the first row by -3 and just summing it to the third row. Right? So in Gauss elimination process, what we do is that we just try to make the entries below the pivot element in each row as zeros. So this is how Gauss elimination works. So what we do is that we try to make the entries below each pivot element as zeros. So if I consider the first row, the first pivot element is 1. So the first job I need to do is that I need to make the entries below this pivot element. What are the entries? That is 2 and 3. I need to make it as 0 by using row operations. So if I want to get this as 2, get this as 0, I need to multiply the first row by -2 and add it to the second. If I want the third entry, the first column as 0, I need to multiply the first row by -3 and add it to the third row. So if I do these operations, you can see that this matrix is nothing but is row equivalent to this. It's nothing but row equivalent to this matrix. Okay. So what I did, I just multiplied the first row by -2, added it to the second row. I multiplied the first row by -3, added it to the third row. So what operations I performed? I just performed the elementary row operations, and therefore I can just make use of this symbol that indicates that they are row equivalent. These two matrices are row equivalent. Okay. So now again, you just consider the pivot element in the second row. We are done with the first row, first pivot element. And you just consider the pivot element in the second row. What is the pivot element? It is 2. Okay. Now try to make all those entries below this pivot element as 0. What are the entries below this pivot element? The pivot element in the second row is 2. So you need to make the entries below this pivot element as 0. So that is, you need to get this -3 as 0. You need to get this -3 as 0. For that, again go for the same process. You just multiply the second row by 3 by 2. You just multiply the second row by 3 by 2 and add it to the third row. Just multiply the second row by 3 by 2 and add it to the third row. So if you perform these operations, so this indeed reduces to, so this matrix will be row equivalent to the following matrix. It is 1, 2, -3, 1, 2, 0, 0, 2, 4, 6. If you multiply by -3 by 2, so you will get it as 0. Here it is 0 and -2. So I just need to multiply it by 3 by 2 actually. So if you multiply it by 3 by 2, so I think this number actually changes. Okay. So therefore this is how you get the echelon form of a given matrix. So here the entries are not correct. I hope this has to be somewhat other. Okay. But anyhow, so this is the procedure how we find out the echelon form of a given matrix. So if you want to know what is the rank of A, then you need to simply count what is the number of non-zero rows. How many non-zero rows are there? There are 1, 2, 3. All the rows are non-zero, therefore the rank of A is 3. So this is an echelon form, and what is the rank of A? Rank of A, it is 3 because the number of non-zero row in its echelon form is 3. The number of non-zero rows in its echelon form is 3. Okay, I hope if you perform it correctly also, then also the rank would be 3 here. So here some mistake is there. I need to multiply it by 3 by 2 into R2 plus R3, not minus 3 by 2. So I need to delete this minus sign. You will be getting its echelon form. So the procedure is to identify the pivot element in a row and make the entries below the pivot element, make those entries as zeros. So in each row you identify the pivot element and make the entries below it as 0. So by using elementary row operations. So this is how you find the echelon form of a given matrix A. Okay. So now, what is its applications to linear systems? What is its applications to system of linear equations? So what is the application of rank when solving a system of linear equations? So of course, it does not give you the solution, but it tells you whether it has a solution or not, or if it has a solution, whether it is finite or infinite, whether it is unique or infinite unique. So before looking into its applications to solving the system of linear equations, let me just give you some preliminaries about what's meant by the matrix representation of a system. So for example, if you just consider a m cross n system of linear equations, a11 x1 plus a12 x2 plus and so on, a1n xn equal to b1. So likewise, if you consider n equations, so suppose if you just consider a m cross n system, that means m equations in n unknowns, okay? Then you can just represent this system of equation in a matrix form as follows. You can just put it in the matrix form as ax equal to b capital B. You can just put it in the matrix form as ax equal to capital B, where capital A stands for the coefficient matrix. So what's meant by the coefficient matrix? It stands for the coefficients A11, A12, A1n, and so on, A21, A22, A2n, and so AM1, AM2, and so on, AM. So this stands for the coefficient matrix. And X stands for the, so this has to be X, not B. So your X stands to be X1, X2, and so on, Xn. Okay, and your capital B, it stands for the constant vector. The constant vector here is B1, B2, and so on, Bn. So this is how you represent the given linear system of equations in the matrix form. We put it in the form of Ax equal to B, where A stands for the coefficient matrix, B stands for the constant vector, X stands for the vector of unknowns. Okay, so from this, this is meant by an augmented matrix. So augmented matrix stands for the matrix A, the coefficient matrix A together with the constant vector B. So this matrix together with the constant vector, it is called as an augmented matrix of the given linear system. Okay. So now I will tell you what is the application of rank in finding out the solution of a system of linear equations, and it is as follows. So if you just consider a linear equations in n unknowns with augmented matrix M, then the system has a solution if and only if the rank of A is equal to rank of M. So if you want to say whether it has a solution or not, the condition is that the rank of A must be equal to rank of M, and the solution is unique if and only if rank of A is equal to rank of M equal to N. Okay, and solution, it has got infinitely many solutions if rank of A is equal to rank of M strictly less than N. So these 2 points are very important while solving the problems. Okay, so the system has a solution if and only if rank of A is equal to rank of M, and the solution is unique if and only if rank of A equal to rank of M equal to N, and it has infinitely many solutions if rank of A is strictly less than rank of, if rank of A is equal to rank of M strictly less than N. So you need to remember these 2 conditions. Okay. So while solving problems based on the system of linear equations, by determining solutions. So far we discussed some preliminaries. Okay, it's not possible to write on all the clear requests in a single slide. you need to have a very broad idea about the subject if you want to solve the problem exactly. So you must be very thorough with the subject and you should be an expert. Okay. So and it's not that you need to go for the routine procedure finding its echelon form and then determine the number of non-zero rows. So you can just use your you can just there are some other ideas. So therefore you can just directly write down what is the rank and find out what is the eigenvalues, all these things. Okay. So let me just consider set of problems and let me just try to explain what is the idea that is that we'll be using to find out the solutions here. So I've just picked this question from your GATE 2015. Okay. So the question it is as follows. You just consider the linear equations. X minus 2y plus 3z equal to 1. X minus 3y plus 4z equal to 1. Minus 2x plus 4y minus 6z equal to k. The question is that the value of k for which the system has infinitely many solutions is. The question is that find the value of k for which the system has infinitely many solutions. So again, if you want to talk about infinitely many solutions, again you need to know what is the rank of the coefficient matrix A and you need to know what is the rank of the augmented matrix. Okay, here I think you can just directly solve this problem, but I will tell you the procedure how to solve. But with little bit, if you are just thorough with this subject, you can directly write down what is the value of k. Okay, there is something. So actually, I will tell you the answer. The answer is the value of k must be equal to 2 if it must possess infinitely many solutions. Why? The reason is why. The question is why. So for this, I have the following argument. Okay. So if you just consider the augmented matrix of the system, what is the augmented matrix? It is 1, minus 2, 3, along with the constant vector 1, 1, minus 3, 4, 1, minus 2, 4, minus 6, k. So this is the augmented matrix. Okay. So augmented matrix, it consists of rows with the entries 1, minus 2, 3, 1. Second row consists of entries 1, minus 3, 4, 1. Third row consists of minus 2, 4, minus 6, k. So now, if you want to discuss about solutions, you just need to find out what is the rank of the coefficient matrix and the augmented matrix. So if you want to know what is the rank, obviously you need to find what is its echelon form. What is the echelon form of the augmented matrix? If you just consider the augmented matrix and try to find out what is its augmented matrix by the method of Gaussian elimination, you can see that its echelon form is as follows. It looks like 1 minus 2, 3, 1, 0 minus 1, 0, 0, 0, k minus 2. So from this, you can find out what is the rank of the augmented matrix and also you can find out what is the rank of the coefficient matrix. So this portion, the portion towards the left side. So this gives you the echelon form of the coefficient matrix A, whereas this whole thing gives you the echelon form of the coefficient matrix, echelon form of the augmented matrix. So this portion, the first half, which I have separated by this symbol, colon symbol, the first half gives you the echelon form of the coefficient matrix, and this whole matrix gives you the echelon form of the augmented matrix. So if you want to find what's the rank of the coefficient matrix, just look into the number of non-zero entries in this first half, right? In the first portion. So what's the number of non-zero entries? It is 2. And so if you want to know if it has a solution, it has an infinitely many solutions. If rank of A is equal to rank of M, it must be less than N. N stands for number of unknowns. What is the number of unknowns here? It is 1, 2, and 3. So it has got infinitely many solutions if rank of A is equal to rank of N strictly less than 3. So that is if K equal to. So when this rank of A, what is rank of A? Rank of A from this portion, you can see that the number of non-zero rows here is just 2, 1 and 2. Rank of A is 2. Okay. And what would be the rank of, therefore obviously the rank of M is greater than or equal to 2. right? Greater than or equal to 2. So therefore, if you want to match it with 2, you must k minus 2 must be equal to 0. In that case, rank of m would be 2. Okay? So your k minus 2 must be equal to 0, therefore the value of k must be equal to 2. So therefore rank of A equal to rank of M equal to 2, strictly less than 3, and hence it has got infinitely many solutions. So therefore the answer, it is 2. So just you need to draw the echelon form of the augmented matrix, and from that you need to write down what is the rank of A. So here the rank of A is 2, and observe that rank of, if you want a solution, if it exists, if only rank of A must be equal to rank of M. So therefore rank of M must also be equal to 2. So if rank of M must be equal to 2, then the last row must be equal to a 0. So therefore k minus 2 must be equal to 0, and hence k must be equal to 2. So therefore since 2 is strictly less than 3, so we can conclude that it has got infinitely many solutions, and hence the answer is 2. Okay. So let me just consider one more question. So this question was asked in our GATE 2018 question paper. The question is as follows. So consider the matrix A, which is given by k, 2k, k square minus k square, and the vector x equal to x1, x2. The number of distinct real values of k for which the equation ax equal to 0 has infinitely many solutions is. The question is to find out the number of distinct real values of k for which the equation ax equal to 0 has infinitely many solutions. So you know what is due to you are provided with the homogeneous system of equations, right? So ax equal to 0, that means system is an homogeneous equation. So where does in case of homogeneous equation, okay, homogeneous system of linear equations, it has got infinitely many solutions if rank of A, if it is less than the number of unknowns. If rank of A is strictly less than unknowns. What I mean to say is that, so if the system of equations is of the form Ax equal to 0, that means the constant vector B is 0, then the system has a solution. If and only if, then the system has definitely has a solution, because 0 itself, the 0 vector itself is a solution. And moreover, it has got infinitely many solutions. It has got infinitely many solutions if rank of A is strictly less than N. So this is with respect to the case of homogeneous linear system of equations. So here the second question is with respect to the homogeneous linear system of equations. So therefore, you know here in this case, you know that the homogeneous system of equations possesses infinitely many number of solutions if rank of A is strictly less than 0. Sorry, strictly less than N, the number of unknowns. What is the number of unknowns here? Is 2. So you need to find the values of K such that rank of A is strictly less than 2. So rank of A is strictly less than 2 means what are the choices for rank? The rank can be either 0, it can be 1, or it can be 2. Because if you are considering a 2 cross 2 matrix, because your A is a 2 cross 2 matrix, you have 3 choices for rank. Rank can be 0, rank can be 2, rank can be 1. Okay? So if it has to possess infinite many solutions, then rank of A must be strictly less than 2. Therefore, you need to look for the cases when rank of A is 0, when rank of A is 1. That's what I have given you in the end. So homogeneous system has infinitely many solutions if rank of A is strictly less than N, the number of solutions, number of unknowns. So here N is 2 because the number of unknowns is 2. So therefore the system has infinitely many solutions if rank of A is less than 2. Therefore, what can be choices for A? Rank of A, it can be either 0 or it can be either 1. So if you just consider the cases when rank of A is 0. Rank of A is equal to 0 means it has got no non-zero rows. It has got no non-zero rows. So that means all the rows are zeros. That means A is a zero matrix. If A is a zero matrix, then only your rank of A is zero. Okay. So rank of A is zero. That means A is a zero matrix. A is a zero matrix provided your K is zero. A is a zero matrix and only if your K is zero. So rank of A is zero. We get it if K is zero. So likewise, rank of A equal to 1. Rank of A equal to 1. So you need to find those values of K for which rank of A is equal to 1. So for this, you need not go for the echelon form and all. So rank of A is 1 means that means the determinant of A is 0. It must be 0. Rank of A is 1. That implies that the determinant of A is equal to 0. That means it must have, the rows must be linearly dependent. Okay, the rows must be linearly dependent. So rank of A equal to 1. So that implies that this is equal to 1 if A is not equal to 0 and determinant of A equal to 0. Okay, rank of A 1 it will be 1 if A is not equal to 0 and the row vectors are linearly dependent. So if the row vectors are linearly dependent, then the determinant of that matrix must be equal to 0. So just find out what is the determinant of A. So what is the determinant of A? It is nothing but simply k square minus 2k cube plus 2k square. So this is the determinant of A. So it must be equal to 0. So again you can just factorize it. So this simply stands for k square into 2 minus k. So it must be equal to 0. Therefore one of them must be equal to 0 and hence your k cannot be equal to 0 because A is not a null matrix. So your k must be equal to 2. So therefore the answer is k must be equal to 0 or 2. And hence the number of distinct real values is 2. Okay? The number of distinct real values of k is 2. See, there are lots of tools that you can use to solve certain problems. It's not based on only one method. Okay? So you need to thoroughly the concept, right? Linear algebra itself is very vast. So you have plenty of techniques to apply and you can easily solve the problems. Okay? So you need to go through all the standard textbooks. So if you want to master in this subject. So let me just consider the third example, the third question, which is asked recently. This question I just picked it from your board GATE 2020. The following question was asked. That is, consider the following system of linear equations: x1 plus 2x2 equal to b1, 2x1 plus 4x2 equal to b2, 3x1 plus 7x1 plus 7x2 equal to b3, 3x1 plus 9x2 equal to b4. The question is that which one of the following ensures that a solution exists for the above system of equations? The condition is that b2 equal to b2 2 times of b1 and 6b1 minus 3b3 plus b4 equal to 0. The second condition is that b3 equal to 2b1 and 6b1 minus 3b3 plus b4 equal to 0. The third and fourth conditions are as follows. The third is b2 must be equal to 2b1 and 3b1 minus 6b3 plus b4 equal to 0. The fourth option is b3 equal to b1 and 3b1 minus 6b3 plus b4 equal to 0. So you need to choose one among these four options. So you need to choose in such a way that those conditions makes this system to have a solution. As well, if you are talking about the solutions, you need to know what is the rank of the augmented matrix as well as the coefficient matrix. Okay. So therefore, first try to find out what is the augmented matrix here. The augmented matrix is 1 2 b1, 2 4 b2, 3 7 b3, 3 9 b4. So write down the augmented matrix and get its echelon form using Gaussian elimination method. Okay, using Gaussian elimination method. Okay. So here, if I just consider the augmented matrix and find out its echelon form using the Gaussian elimination method, I can see this picture. I have this picture. Okay. Actually, I need to delete this equal to 0. It's not there. It is simply 1, 2, B1, 0, 1, B3 minus 3, B1, 0, 0, 6, B1 minus 3, B3 plus B4. So this equal to 0 is not there. I'm sorry for that. So the last row would be 0, 0, B2 minus 2, B1. So this is the echelon form of the augmented matrix of the given system. So equal to 0 is not there, it's a typo error. Okay. So now we just have a look into the rank of the coefficient matrix. That is the first part. Leave these constant terms, consider this matrix. What's its rank? Rank stands for the number of non-zero rows. So its rank is just 1 and 2. Its rank is 1 plus 1, 2. So rank of the coefficient matrix is 2. And you just consider what is the rank of the augmented matrix. So you know the rank of the augmented matrix, it's again, it is at least 2 because the non-zero rows here at least it's at least 2. So you want to know, you know that it has a solution if both the ranks are same. If both the ranks are same, that means the last 2 rows must be equal to 0. I repeat. So here what I did is that I just consider the augmented matrix of the given system. And then I just written its echelon form using this Gaussian elimination method. So after finding this echelon form, I first observe what is the rank of the coefficient matrix, that is rank of A. So rank of A is nothing but the number of non-zero rows. It is 2A, so the rank of A is 2. And then I just look into what is the rank of the augmented matrix. You know, the rank of the augmented matrix is obviously it is at least 2 in this case because it's coming from these first 2 rows, right? So you want, if it has a solution, then rank of A must be equal to rank of M. Okay. So rank of A is 2. You want now rank of M also should be equal to 2. But you know rank of M is at least 2. So therefore, if you want it to be equal to 2, then the last 2 rows must be equal to 0. Last 2 rows must be equal to 0 means your B2 must be equal to B2 minus 2B1 must be equal to 0. That is your B2 must be equal to 2B1. And also your 6B1 minus 3B3 plus B4 must be equal to 0. So here it's not there equal to 0. But if these 2 conditions are true, then it has a solution. So therefore, the choice for you need to just round off the option A. So option A is the correct answer. The next question is as follows. I just picked it from your GATE 2017. So it's directly asked to find what is the rank of the matrix 5, 10, 10, 1, 0, 2, 3, 6, 6. See, no need of writing down the echelon form and when you have a simpler one, right? See here directly you can observe rank actually stands for the number of linearly independent rows in a matrix. Linearly independent row in a matrix. You can see that from the given the matrix, you can easily see that the first row and this last row. The first row, what is the first row? It is 5, 10, 10, and the last row it is 3, 6, 6. They are not linearly independent; they are dependent. Right? The first row and the last row they are linearly dependent. It's a multiple of each other. Linearly dependent means here in this case, it's they are multiple of each other. So this simply stands for 5 times of 1, 2, 2. The third row simply stands for 3 times of 1, 2, 2. Right? So the first and this third row they are linearly dependent. And also you can note that therefore the rank should be is not 3, that is confirmed. So since the first row and the second row, last row are dependent, the rank is not 3. Okay, if it is 3, that means all these 3 rows must be linearly independent. Here, the first row and third row, they are linearly dependent. So, rank is not 3. So, it can be either 1, it can be either 2. So, it's of course, it's not 1 because of this 1, 0, 2. So, if you just compute what is the determinant of this submatrix 5, 10, 1, 0, of course, it is non-zero. So, therefore, we can easily write down that rank of the matrix, the given matrix is 2. So these are the options 2, 1, 3, 0. So if you just look into this matrix, the first and third rows they are linearly dependent. That means the rank of the matrix is not 3. And also you can just look into this submatrix 5, 10, 1, 0. Their determinant is non-zero. So therefore, you can say that the first and second row they are linearly independent, and hence the rank is 2. The maximum linearly independent row is 2 in this case, and hence the rank is 2. Or else, if you are not getting this, also you can just write down its echelon form. From there, you can conclude what's the rank. So it's not always suggested to go for the usual technique, because you need to save your time also. So here, these are all direct questions. You can answer it directly without any work. Again, here in this case, again you are asked to find out what is the rank of the matrix 1, -1, 0, 0, all these things. So here you need to write down the echelon form. Of course, there are other methods which depends upon the eigenvalues. But here you can easily write down the echelon form. It's not difficult. Okay. So if you want to know what is the rank of this matrix, you just need to write down what is its echelon form. The question is as follows: the rank of the matrix is option A 2, option B 4, option C 3, option D 1. So again, you just write down what's its echelon form. So if you just go for this quotient elimination, so you can just easily write down its echelon form. So this is the echelon form of the given matrix. So if you look into this echelon form, the number of non-zero rows, what is the number of non-zero rows? It's 1, 2, 3, 4. Right? So the number of non-zero rows is 4, and hence you can conclude that the rank is 4. Okay? So I told you how to just get the echelon form of the given matrix. So you just consider the pivot element. First, you just consider the pivot element. Here, the pivot element in the first row is 1. So make all the entries below it as 0. That means you need to get this -1 as 0. So therefore, you need to just multiply the first row by, just add the first row with the fourth row, with the third row. So you can get this as 0. So likewise, you just find out the pivot element in each row and make all those entries below that pivot element as 0. So this is how Gaussian elimination is. This is what Gaussian elimination is. Okay. So if you do that, you can see that the echelon form of the given matrix is as follows. From this, you can conclude that the rank is 4 because the number of non-zero rows here is 4. So this completes this problem of number 5. So next, let me just talk about the eigenvalues and eigenvectors. So for finding the rank and finding the solutions of a linear system, so it mainly depends upon the condition that rank of A must be equal to rank of M. In that case, it has got a solution, and moreover, the solution is even unique if rank of A is equal to rank of M strictly less than N, and it has got infinitely many solutions if rank of A is equal to rank of M strictly less than N, where N stands for the number of unknowns, where N stands for the number of unknowns. So next let me just move on with the eigenvalues and eigenvectors. So you have studied all these topics, eigenvalues and eigenvectors in your lower semesters, right? So let me just quickly brush up what's the definition of an eigenvalue and eigenvector. So if you just consider a square matrix of order n, then a scalar lambda is said to be an eigenvalue of A. Then a scalar lambda is said to be an eigenvalue of A. If there exists a non-zero vector V, such that A times V equal to lambda times V. That is A times V equal to lambda times V. So if there exists such a non-zero vector, then we say that lambda is an eigenvalue of the matrix A, and this non-zero vector V is called an eigenvector. It is called as an eigenvector corresponding to the eigenvalue lambda. This non-zero vector V is called as an eigenvector corresponding to the eigenvalue lambda. So there are certain equivalent definitions. Equivalently, eigenvalues of a square matrix are nothing but the roots of the characteristic polynomial or the roots of the characteristic equation, determinant of A minus lambda in equal to 0. And the eigenvectors corresponding to the eigenvalue lambda, eigenvalues, eigenvectors corresponding to the eigenvalue lambda, they are nothing but the solution space of the system A minus lambda n of x equal to 0. They are nothing but the solution space to the homogeneous system A minus lambda n of x equal to 0. So both the definitions they are equivalent, right? Both the definitions they are equivalent. You can easily observe that. So therefore, by an eigenvalue, we just mean root of this the root of this characteristic equation, that is determinant of A minus lambda n equal to 0. So therefore, so how many eigenvalues does the square matrix of order n have? So that's the first question comes into mind. How many eigenvalues can I find out for a given matrix A, or how many eigenvalues does the square matrix have? So from this singular definition, you can see that that simply stands for the roots of the characteristic equation, determinant of A minus lambda n equal to 0. So this equation indeed it stands for a polynomial of degree n. This stands for a polynomial of degree n, and hence it can have at most n roots. It can have at most n distinct roots. Okay. So therefore, the number of eigenvalues associated with the square matrix A is n. Right? We can have n number of eigenvalues. And as I told you, the eigenvectors corresponding to the eigenvalue lambda, they are nothing but the solution space of the system A minus lambda n of x equal to 0. Okay, let me just consider the problem here. Okay, just consider the problem is as follows. Consider the matrix A as shown. It is given that A has only one real eigenvalue. It is given that A has only one real eigenvalue. Then what is the real eigenvalue of A? So the problem is made very easier by stating that it has got only one real eigenvalue. Just have a look into the matrix. So it's all 1, 2, 3, 4, 5, 5, 1, 2, 3, 4. That is the second row. The third row is 4, 5, 1, 2, 3, and so on. So if you just look into this matrix, so what is the sum of each row? What is the sum of each row? The sum of the first row, it is simply 1, 2, 3, 4, 5. So what is the sum? It is just 50. The sum of the second row, again it is 50. The sum of the third row, again it is 50. The fourth row, 50. Fifth row, 50. So what does this actually implies? It implies that 15 is an eigenvalue of the matrix A. Why? Because if you set the vector V as the column vector with all entries as 1, then that is an eigenvector corresponding to the eigenvalue 15. Just if you multiply this matrix A by the column vector with all entries as 1, so you will be getting this is equal to 15 times. This is equal to, that would be equal to 15 times the column vector with all its entries as 1. So and hence you can conclude that 15 is an eigenvalue of the given matrix A. So in general, if all the row sum is equal to a constant k, in general, if all the row sums, if the row sums of a matrix, if it is equal to a constant k, then it is understood that k is an eigenvalue of the matrix, and the column vector with all its entries as 1 is an eigenvector. It is easy to see. So since it is given that it has got only one real value, and you know that 15 is an eigenvalue, then your answer is 15. The options was 2.5, 0, 15, 25. So since the sum of each row here it is 15, so it is understood that 15 is an eigenvalue. Therefore, option C is correct. right? So likewise, if the sum of each sum of entries in a column, if they are constant, again that would be an eigenvalue. So their answer is 50. See, there are a lot to learn about this. It's not just a few problems, right? So you need to know a lot of things here. So the question number 7 reads as follows: the value of x for which the matrix has 0 as an eigenvalue. The value of x for which the matrix A equal to 3, 2, 4, 9, 7, 13, minus 6, minus 4, minus 9 plus x as 0 as an eigenvalue is option A 1, option A 1, option B 2, option C 3, option D 4. The value of x for which the matrix A has 0 as an eigenvalue is option A 1, option B 2, option 3, option C 3, option D 4. So what's the idea here? If you want to crack this problem, what's the idea? So you need to know that 0 is an eigenvalue of any matrix. You need to know that 0 is an eigenvalue of any matrix if and only if the determinant of A is 0. If and only if the determinant of A is 0. So, yeah, that is the first point you need to remember here. That is, 0 is an eigenvalue of a square matrix if and only if the determinant of A is 0. So, when does this determinant of A is 0? Determinant of A is 0 if and only if the row vectors are linearly dependent. The row vectors are linearly dependent. So in that case, the determinant of A will be 0. So for the problem is to find out the value of x such that these rows are linearly dependent. Okay? These rows are linearly dependent. So what is the choice for x such that these three rows are linearly dependent? So that's our next problem. So now we just observe the first row and the last row. Just observe the first row and the last row. But don't you think that the last row is a multiple of the first row? You can choose x in such a way that the last row is a multiple of the first row. So for example, if I multiply the first row by minus 2, I will be getting minus 6. The second entry I will be getting it as minus 4. The third entry, if I am able to get it as minus 8, so then I am done. So therefore, your x should be such that minus 9 plus x should be equal to minus 2. Minus 9 plus x should be equal to minus 2. Therefore, what's your x? Your x should be your minus 9 plus x must be equal to minus 2. So what's the value of x then? It has to be 9 minus 2, that is 7. 9 minus 2. So here the problem is to find out the value of x such that the rows are dependent. So first observe that the first row and the second row you can make it as a dependent one. So if you just multiply the first row by minus 2, so it is simply minus 6. The first entry will be minus 6. The second entry will be minus 4. The third entry it is minus. So here you get it as minus 8. Therefore your minus 8 must be equal to minus 9 plus x. So minus 9 plus x must be equal to minus 8. So therefore the value of x must be equal to 1. So therefore option A is correct. That is answer, the value of x must be equal to 1. So what was the idea that I used is that the fact that 0 is an eigenvalue of a matrix A if and only if its determinant equal to 0. This, therefore, no need of finding the determinant of A actually. So determinant of A would be 0 if the rows are linearly dependent. Just look for those values of X. Just idea is to just have a look into the first row and the second row. You can make it dependent by a suitable value by choosing a suitable value for X. So if you multiply it by -2, you will be getting -6, -4, the second entry, fine. Here it will be -8. Therefore, if this entry, if it is -8, then the first and the last row is dependent. So therefore, make this -9 plus 8 equal to -8, and hence X must be equal to 1. So option A is correct in this case. See, again here, this doesn't mean that you need to find out what is the determinant of this 3 cross 3 matrix. You need to know what is when this determinant of A is 0. It is 0 if they are linearly dependent. Let me move on with the next question. So the next question is as follows. The value of X for which the matrix A, value of X for which the matrix A 10, 5 plus I, 4, X 20, 2, 4 minus 10 as real eigenvalue only. The value of X for which the matrix A 10, 5 plus I, 4, X 20, 2, 4 minus 10 as real eigenvalue only. So before looking into this, solving this problem, you need to know one point is that, so if you have a real symmetric matrix, then all its eigenvalues are real. So this is the point number 1 you need to know. A real symmetric matrix has real roots. Likewise, a skew symmetric matrix has purely imaginary roots, purely imaginary eigenvalues. So likewise, an Hermitian matrix, it has got only real eigenvalues. Hermitian means A conjugate transpose must be same as A. A conjugate transpose must be same as A. So if A conjugate transpose A conjugate, I mean need to take the conjugate of each of the entries in the matrix, and then you take the transpose. If A conjugate will transpose it is equal to A, then we say that matrix is an Hermitian matrix. So note that here, so it's almost looks like an Hermitian matrix, only choice for X is missing. So the options are as follows. A is 5 plus I, B is 5 minus I, C is 5, D is minus 5. These are the other options. So, and you know the fact that an Hermitian matrix, all its eigenvalues are real. So you can just pick a value of X in such a way that this matrix A is an Hermitian matrix. So if you pick C equal to 5, if you pick X equal to 5, then the matrix is not Hermitian, you can verify, because A conjugate transpose is not same as A. If you pick A as minus 5, again not. And also if you pick X as 5 plus I, again it's not an Hermitian matrix. So therefore correct option is 5 minus I. So if you choose X equal to 5 minus I, so then this matrix A will be a Hermitian matrix. That is, A conjugate transpose is equal to A. Conjugate, I mean, you need to take the conjugate of each of the entries. What is the conjugate of 10? It is 10. What is the conjugate of 5 plus I? It is 5 minus I. The conjugate of 4, it is 4. So in general, what is the conjugate of A plus IB? It is A minus IB. So first you need to take the conjugate of each of the entries, and then you just take the transpose of that matrix. If that is equal to the parent matrix, that is A, then we say that the matrix A is Hermitian. So the point to be remembered here is that Hermitian matrix will have real eigenvalues. So therefore, the only choice here it is 5 plus I. For this choice of X, you have A as A as a Hermitian matrix, and hence the choice is the correct option is 5 minus I, that is option B. That's what I have written here. So the next is again, it's one of the simple question. The value of x for such that the vector 1, 2, 3 is an eigenvector for the matrix A. So you are asked to find out what is the value of x such that this column vector V, will be an eigenvector for the matrix A. Will be an eigenvector for the matrix A. So you know what from the definition of an eigenvalue. So you know when you are going to say that a scalar lambda is an eigenvalue of a matrix A. Just make use of the definition here. So you want to determine the value of x such that the column vector V is an eigenvector. So what does definition tells you? So V, if it has to be an eigenvector, then AV must be equal to lambda into V. If you want to say that V is an eigenvector, then your A into V, what is A into V? So multiply A by V, so it is just 4 plus 1 plus 2. So 4 plus 2 plus 6, so it is 12. Here it is x plus 4 plus 3, that is x plus 7. Here it is 36. Here it is 36. So it must be equal to lambda into V. So this is the condition for a column vector to be an eigenvector. Okay. So your AV must be equal to lambda into V. So I just computed what is AV in this case. A times V is the column vector 12, x plus 7, 36. This must be equal to lambda times 1, 2, 3. So you are saying that these two matrices, they are one and the same. So therefore these two matrices must be equal to one and the same. When you say that two matrices are one and the same, two matrices are one and the same if their corresponding entries are equal. If their corresponding entries are equal. So therefore, your 12 must be equal to lambda into 1, your x plus 7 must be equal to 2 lambda, your 36 must be equal to 3 lambda. So you just from this you can note that 12 must be equal to lambda into 1, that is lambda must be equal to 12, and your x plus 7 must be equal to 2 lambda. So lambda is 12, so therefore x plus 7 must be equal to 24. Your x plus 7 must be equal to 24. So therefore the value of x should be 17. Therefore the value of x should be the definition of an eigenvector. So you need to remember that a non-zero column vector V is said to be an eigenvector if AV equal to A times V equal to lambda times V for some scalar lambda. So if you make use of this definition, you get this matrix equation. So from this matrix equation, you understand that each entries, corresponding S2 entries must be one and the same. So here the entry 12 must be equal to lambda times 1 and x plus 7. This entry must be equal to 2 times of lambda. So from the first equation, you know that lambda is 12. And if you substitute this in the second equation, that is x plus 7 equal to 2 lambda. So you will be getting that x plus 7 equal to 24 and hence x equal to 24 minus 7, that is 17. So this is an interesting question. So it was asked in our GATE 2018. The question is as follows: that MBA real 4 cross 4 matrix. Like MBA real 4 cross 4 matrix. Consider the following statements. Statement 1 is that M has 4 linearly independent eigenvectors. M has 4 distinct eigenvalues. M is non-singular. Non-singular means invertible. Which one among the following is true? Option A is S1 implies S2. Option B is S2 implies S1. Option C is S1 implies S3. Option D is S3 implies S2. You need to read these statements S1, S2, S3, and you need to identify which one of the following option is true. That is whether S1 implies S2, S2 implies S1, S1 implies S3, or S3 implies S2. So first let me just read out what is the statement M stands for. Statement S1 stands for. It tells you that M has 4 linearly independent eigenvalues. M has 4 distinct eigenvalues. Statement 3 is M is non-singular. So let us just come to the first option, that is S1 implies S2. If M has 4 linearly independent eigenvectors, do that implies that M has 4 distinct eigenvalues? If M has 4 linearly independent eigenvectors, do that implies that M has 4 distinct eigenvalues? This is not true. S1 does not imply S2. S1 does not imply S2. Why this is the case? Because if you consider the diagonal matrix, with all its diagonal entries as 1, okay, then of course all its diagonal entries are 1. Then what are its eigenvalues? Then its eigenvalues are nothing but diagonal entries. So in general, if you consider an upper triangular matrix or a lower triangular matrix, its eigenvalues would be the diagonal entries, right? So obviously that S1 need not imply S2. That means if M has 4 linearly independent eigenvectors, then it may not implies that M has 4 distinct eigenvalues. For example, you can just work out with the matrix, the diagonal matrix, with keeping all the diagonal entries as 1 or 2. Okay, because there it has got only one eigenvalue, only one distinct eigenvalue, that is 1, and moreover it has got 4 independent eigenvectors. Okay, so that's not true. So S1 does not imply S2. So the second option is that S2 implies S1. S2 implies S1 means, what is S2? M has 4 distinct eigenvalues. Do that implies that M is non-singular? No. It has got nothing to do with the singularity. The distinct number of eigenvalues, it has got nothing to do with the singularity. Okay? So if S2 was that 0 is an eigenvalue, then it necessarily implies that M is non-singular. So simply saying that M has the singularity of the matrix. So S2, here S2 need not implies S3 actually. So option B is S2 implies S1. Okay. Option B is S2 implies S1. That means M has 4 distinct eigenvalues. Do that implies that M has 4 linearly independent eigenvectors. Option B is as follows. Sorry, I have just misinterpreted with S2 implies S3. So it is just S2 implies S1. So S2 is M has 4 distinct eigenvalues. Whether this implies that M has 4 linearly independent eigenvectors? Of course, yes. Of course, yes. Because so each distinct eigenvalues gives you distinct eigenvalues in a matrix of a matrix gives you a linearly independent eigenvectors. Since it has got 4 distinct eigenvalues, therefore they indeed gives 4 linearly independent eigenvectors. So option B is correct actually. So option B is correct. Okay, now let me just option B is right. So therefore you need to mark B because only one answer will be correct. Okay. So S1 implies S3. That means M has 4 linearly independent eigenvectors implies M is non-singular. So eigenvectors it has got no link with the singularity of the matrix. So option C is not true. S3 implies S2. M is non-singular. It implies M has four distinct eigenvalues. No, this is also not true because the singularity of a matrix it does not depend upon the number of distinct eigenvalues. Okay. So therefore, the correct option here is S2 implies S1. That means if M has four distinct eigenvalues, then M has four linearly independent eigenvectors. So this is because each of the distinct eigenvalues gives you an independent eigenvector to the collection of eigenvectors. Okay, and hence total 4. So the 4 S2 implies S1. Okay. So here, question number 11. So it's taken it from your gate 2019. We are supposed to find out the number of distinct eigenvalues of the matrix A, which is given as follows: 2, 2, 3, 3, 0, 1, 1, 1, 0, 0, 3, 0, 0, 2. So in matrix, you have come across this matrix while I think while we are discussing with this matrices, right? This is one of the familiar matrix. It's called as an upper triangular matrix, right? So, so it is an upper triangular matrix. Just now I told you that if you have any upper triangular or a lower triangular matrix, then its eigenvalues are nothing but the diagonal entries. The eigenvalues are nothing but the diagonal. Just looking into the matrix, you can see that it's an upper triangular matrix. It's an upper triangular matrix. It's 2, 1, 3, 2. 2, 1, 3, 2. So these are its diagonal entries. So as I told you, if you are looking for the eigenvalues of an upper triangular or a lower triangular matrix, then its eigenvalues are nothing but the diagonal entries. So therefore, the eigenvalues of this matrix are nothing but 2, 1, 3, 2. They are nothing but 2, 1, 3, 2. How many of you find? How many of them are distinct? It's just 1, 2, and 3. So therefore, the number of distinct eigenvalues of the matrix is 3. You have 4 eigenvalues, out of which 3 is distinct. Okay. So now let me just consider one more set of problems from your date 2020. So the question is as follows. If you consider 6 vectors in R4, in the space R4, 4-dimensional space, okay? If you consider 6 vectors, V1, V2, and so on, V6, are 6 vectors in R4, which of the following statements is false? Is false. Which of the following statements is false? Option A, it is not necessary that these vectors span R4. These vectors are not linearly independent. Option B. C. Any 4 of these vectors form a basis for R4. Option D is that if V1, V3, V5, V6 spans R4, then it forms a basis for R4. Then it forms a basis for R4. Which of the following statement is false? You need to pick a wrong one here, the wrong statement. Okay, let me just, what's meant by a span, a linear span. Linear span of vectors. Suppose I just consider 2 vectors, say U and V. Then by the linear span of these 2 vectors, U and V, I mean the collection of all elements U, alpha into U plus beta into V for any scalars alpha and beta in R. Okay, so by a linear span of vectors, I mean just a linear combination. I just mean a collection of all linear combinations of the vectors. So the first option is as follows. It is not necessary that these vectors span R4. Of course. So if you want that to span R4, so you know that if you consider the space Rn, an n-dimensional space Rn, then it's of dimension n. That means it is spanned by n number of linearly independent vectors. That means its dimension is n. That means to say that the maximal linearly independent vectors in that space is, the count is n. So it is not necessary that this vector span R4 is 2, because I can set all these vectors v1, v2 and so on v6 equal to some constant vector v. Okay. So therefore this single vector will not span R4. So if you want to span R4, you need to have 4 linearly independent vectors. 4 linearly independent vectors spans R4. Okay. Now if I say that v1, v2 and so on v6 equal to v, a single vector, then it independently cannot span R4. Hence first statement is correct. That means it is not necessary that these vectors span R4. Fine. So now just come to the second statement. These vectors are not linearly independent. These vectors are not linearly independent. So you know, if I talk about the space Rn, then the maximal linearly independent set, the maximum number of linearly independent vectors you get is n. That's what the dimension is. Okay, if I talk about R2, then you can find 2 linearly independent vectors in the space R2. If you consider the space R3, then you can find exactly 3 linearly independent eigenvectors. Maximum number I'm talking about, not the minimum. Okay, so if you consider R5, you can have 5 up to 5 linearly independent linearly independent vectors you can find. So therefore, in the case of R4, you can find at most 4 linearly independent vectors. So here, if all of this happens to be linearly independent, then R4 has 6 linearly independent vectors, which is not true, because R4 has the maximum number of linearly independent vectors in R4 is 4. So therefore, these vectors are not linearly independent. This is correct. Okay. Now let us just come to the option C. Option C is as follows: any 4 of these vectors form a basis for R4. So first let me tell you what is meant by basis of R4. Basis of R4, I mean the maximal linearly independent subset of R4. By a basis, I mean a set of linearly independent vectors which indeed spans R4. For example, if I consider the space R2, then its basis would be 1, 0, 0, because with the help of the point 1, 0 and 0, 1, I can just span whole space R2. And if I talk about R3, the basis, an example for the basis would be 1, 0, 0, 0, 1, 0, 0, 0, 1. So these bases are always referred as standard basis. So this indeed spans, this indeed is a basis of R3. So likewise, you can just write down the basis for R5, R6 also, all these things. Okay. So here, the statement is that any 4 of these vectors form a basis for R4. So it is not necessarily true. For a basis, the first condition is that it must be linearly independent and then it must span R4. Okay. So it is not necessary that the considered vectors, that is v1, v2 and so on, v6, they are linearly independent. Any 4 of them, they may not be linearly independent, because you can say v1, v2 and so on, v6 equal to a constant vector. Okay. So that indeed it won't span R4 and hence it is not a basis. So therefore option C is wrong. So the next option is D. Therefore if A, B, C are wrong, if A, B, C are, if A and B are correct, so here C is, that is any 4 of these vectors form a basis. So this is not true. Option C is not true. So because this may be linearly independent, for a basis it must be linearly independent. Of course 6 vectors won't span. Of course any 4 vectors, they may be, all the vectors they might be dependent. So therefore option C is wrong. That means it's a false statement. So therefore, you need to tick mark this option C. That means you need to round off this option C. So that is actually a false statement. So let us have a look into the option D. So let us justify why it is correct. So if V1, V2, V3, V1, V3, V5, V6, V1, V3, V5, V6, if it spans R4, space R4, then forms a basis for of course. So this is true because R4 is a dimension. R4 is of dimension. It's of dimension 4. R4 is of dimension 4. That means so here it is given that V1, V3, V5, V6 spans R4. Therefore, a subset of this set, would be a basis for R4. What's the subset of this set? It can be a proper set? No. A proper set would be of dimension 1, 2, 3. Right? So therefore, it cannot be a proper set. It has to be this set itself. And hence it is a basis. So option B is right. So therefore, the correct answer for this question is option C. The correct answer for this question is option C. Okay. So before moving to the next topic, actually, I need to talk about other problems related with the system of equations. Suppose, and with respect to the first question, if the question was like this, find the value of k for which the system has no solutions. Find the value of k for which the system has no solutions. Then, how do you conclude this? How do you just determine the values of k? Find the values for which the system has no solutions. So again, as usual, we will write down the augmented matrix and find out its echelon form using the Gaussian elimination process. So you can note that, one thing you need to note that the system, it has got no solution if its echelon form, if the echelon form of the augmented matrix, if it has a row of the form 0, 0, 0, B with B not equal to 0. So keep this in mind, this point in mind. The system, it has got no solution if the echelon form of the augmented matrix, if it has a row of the form 0, 0 and so on, all zeros, with the last entry B not equal to 0. Therefore, if the question was to find the value of k for which the solution has infinite, for which the solution system has no solution, then your k must not be equal to 2. If k is not equal to 0, if k is not equal to 2, then it has got a row of the form 0, 0, 0, 0, B not equal to 0, and hence it has got no solution. You can directly see that there is no solution for that. Okay, that is one point I need to tell you about the solutions. And regarding the rank, as usual, sometimes you can find out rank also stands for the number of non-zero eigenvalues. Right? It can also relate with the eigenvalues. Rank stands for the number of non-zero eigenvalues. Okay. So this is a nice little say. It's coming from the rank entity theorem. It's coming from the rank entity theorem. Okay. So that stands for the number of non-zero eigenvalues. And regarding eigenvalues, an upper triangular matrix, it's an upper triangular matrix or lower triangular matrix, that eigenvalues will be the diagonal entries. And certain things you need to read more about basis, dimension. So for example, if you consider a n cross n matrix, then what is its dimension? What are bases? All these are very basic things you need to know. For example, if you consider a polynomial of degree 2 or degree 3, if you consider a set of all polynomials of degree 2, degree 3, what are its bases, what is its dimension? Okay, all this matrix space, you can just put it in the form of the vector. So all these things you need to know. There are plenty of things you need to talk. One can talk about this linear algebra. You need to know what is meant by canonical forms, the linear transformations, right? The subspaces, the addition of two subspaces, what's its dimension, rank and nullity theorem. There are a lot of things to learn under this topic, linear algebra. But so time is not permitting me to just go further with that topic. For time being, let me just start with the next topic, that is the higher order differential equation. Because I found some questions are coming from this topic, higher order differential equation. That's why I just picked up this topic, higher order differential equation. Okay, higher order ordinary differential equation, more precise. So let me just start considering a second order ordinary differential equation with constant coefficients. So ordinary differential equations, here we have only one dependent variable with respect to an independent. Here we have a dependent variable with respect to only one independent variable. Okay. So you just consider a second order differential equation with constant coefficients. How does it look like? It looks like this. It looks like a into b square y by dx square plus b dy by dx plus c y of x equal to r of x. I just consider a second order differential equation. Its general form is as follows. So with constant coefficients. So now I am interested to find out what are its what is its general solutions. What is its general solutions? Okay. So I just moved on from the topic linear algebra to this differential equations. So for this, I have just chosen the higher order differential equation, wherein I have just considered a second order ordinary differential equation with constant coefficients. So this method you can just generalize it with the higher order differential equation. So for the sake of simplicity, I have just considered the second order ordinary differential equation. Okay. So this equation using the d operator. So d operator means it stands for d by dx. So you can just put it as follows. You can just put it as f of d by y equal to r of x. Using the operator, where d stands for d by dx, you can just rewrite the second order differential equation as follows. You can just put it as f of d into y equal to r of x. So what is this f of d? So if you make use of this d operator, your d square by dx square, d square by dx square will be d square, and d by dx will be capital D. So that's the thing that happens if you just make use of this d operator. Your d square by dx square will be d square, capital D square, and d by dx will be simply capital D. So therefore you can just put it in the form of f of d into y equal to r of x. What is f of d therefore? Your f of d stands for a d square plus bd plus c. So this is your f of d. So using the operator, you can just represent this differential equation as follows. That is simply a d square plus bd plus c into y equal to r of x. Okay. So its general solution, we all know that its general solution is divided into two pieces, two parts. That is its general solution y of x is given by yp plus yc. It is given by yp plus yc. So what is this yp actually stands for? Yp stands for the particular integral or the particular solution. And what is this yc stands for? Yc stands for the complementary solution. YC actually stands for complementary solution of the given differential equation. YP stands for the particular solution or particular integral. So if you just solve it for y, so you can easily note that y is nothing but r of x by f of t. This is just a notation for yp. Okay, this is just a notation for yp. Usually yp is denoted by this. So how do you remember this notation? We just simply solve this equation for y. So y is nothing but r of x by f of t. So let's we denote yp by this notation, that is r of x by f of t. And the complementary solution, what is this? What's meant by this complementary solution? So complementary solution, I mean the general solution of a homogeneous differential equation. Complementary solution means I mean a general solution of the homogeneous differential equation f of dy equal to 0. If r of x equal to 0, then that equation will be called as an homogeneous differential equation. So here your YC simply stands for the general solution of f of dy equal to 0. So now I will tell you how to find out this YC. So let me just quickly summarize what I have taught you so far, what I just brought to you. Okay. The first thing is that here I am just looking for the solution of higher order differential equation. So to understand, I will just consider a second order ordinary differential equation with constant coefficients, and with the help of d operator, that is d equal to d by dx, I am able to rewrite it in the form of f of dy equal to r of x. Okay, we all know that its general solution is divided into two parts. The one is yp, other part is yc. So your yp actually stands for the particular solution, and it is usually denoted by this notation, that is r of x by f of d. And yc, it stands for the complementary solution of f of d y equal to r of x. That is, yc is the general solution of the homogeneous differential equation f of dy equal to 0. So now I will tell you how to find out what is find out yc. So if you want to find out what is yc, then you need to write down the auxiliary equation. So just consider the auxiliary equation. So auxiliary equation here is auxiliary equation, I mean the equation f of d equal to 0. Auxiliary equation, I mean simply f of d equal to 0. Consider the auxiliary equation, find its roots. If you say that roots are m1 and m2, so since I have considered a quadratic equation, so since I have considered a second order differential equation, it has got only two roots. If you say that m1 and m2 are the only two roots, are the two roots of the auxiliary equation f of d equal to 0, then the general solution of the homogeneous equation f of dy equal to 0 is divided into these three cases. It's divided into these three cases. So cases are as follows. If m1 and m2 are distinct, then yc, that is the complementary solution, that is yc is given by c1 into e power m1x plus c2 e power m2x. So if m1 is not equal to m2, then yc is given by c1 e power m1x plus c2 e power m2x. If the roots are one and the same, that is if m1 equal to m2 equal to m, if m1 equal to m2 equal to m, then your yc is simply e power mx into c1x plus c2. So you need to remember this table. Okay, if m1 is same as m2 equal to m, then your yc is e power mx into c1x plus c2. And if the roots are complex, you know that complex roots, they always occur in conjugated pairs. Complex roots, they always occur in conjugated pairs. That is, if m1 and m2, if it's of the form of a plus or minus ib, then if it's of the form of a plus or minus ib, then yc is given by e power ax c1 cos bx plus c2 sin bx. Okay, so this is actually the idea of formulas to just find out yc. This is the idea of three cases. So depending upon which you can write down what is yc is. Okay. For example, if you consider f of d equal to d square plus d minus 2. So if f of d is d square plus d minus 2, then what are its roots? You can easily verify that its roots are 1 and minus 2. You can easily see that its roots are 1 and minus 2. The roots are real and distinct. And hence its solution will be y1 c1 e power m1x. What is m1? It is 1 plus c2 e power m2x. m2 is minus 2. So therefore, yc is simply c1 e power 1x plus c2 e power minus 2x. Okay, fine. So now let me consider few more examples. Suppose if your f of d, that is the auxiliary equation, it is 4d square plus 4d plus 1 equal to 0. Then what are its roots? So you can easily see that its roots are nothing but minus 1 by 2 and minus 1 by 2 repeated twice. That means the roots is minus 1 by 2 repeated twice. So in this case, this comes under the case 2. That means if the roots are same, that is m1 equal to m2 equal to m. So in this case, your yc So yc is simply given by e power mx. Here m is minus 1 by 2. So it is e power minus 1 by 2 into x. It is e power minus x by 2 into c1x plus c into c1x plus c2. And if the roots are complex conjugate, that means if I just consider f of d equal to d square plus d plus 1, if I consider f of d equal to d square plus d plus 1, then its roots are complex conjugates. Its roots are nothing but, so this stands for the cube roots of 1, they are nothing but minus 1 plus or minus I root 3 by 2. If you just solve this equation for t, you can see that its roots are nothing but minus 1 plus or minus I root 3 by 2. Okay, so what's your A in this case? Your A is minus 1 by 2. And what's your B? B stands for root 3 by 2. So therefore, and hence your YC. So it is e power ax into c1 cos bx plus c2 sin bx. So it is therefore it is e power minus x by 2 into c1 cos b. B is root 3 by 2. Therefore it is cos root 3 x by 2 plus, so it's a typo error here, we need to delete 1 plus, okay, plus c2 sin root 3x by 2. So this is the solution. That means this stands for the general solution of a homogeneous differential equation. Okay. So now let me just consider a question from your GATE examination. Right. I just consider one question. Yeah, the question is as follows. This I have picked it from your GATE 20. Yeah, maybe GATE 2020. Yeah. So here you can just look into the screen. That question is solved recently. So there was one question based on this error differential equation. Actually, it was there, but I am missing. Yeah. So just look at this question number 4. Just looking at this question number 4. You are asked to find the general solution of. You are asked to find the general solution of. You are asked to find the general solution of the differential equation d square y by dx square minus 6 dy by dx plus 9y equal to 0. So what does this equation looks like? It looks like a second order ordinary differential equation with constant coefficients, which was just now we learned about that, how to solve a second order ordinary differential equation with constant coefficient. Here it is the same. This is the second order ordinary differential equation with constant coefficients. That is d square y by dx square minus 6 dy by dx plus 9y equal to 0. And the options are as follows. Option A is y equal to c1 e power 3x plus c2 e power minus 3x. Option B is y equal to c1 plus c2x into e power minus 3x. Option C is y equal to c1 plus c2x into e power 3x. Option D is y equal to c1 e power 3x. Okay. So the idea to solve here, it is the homogeneous differential equation. So there is no yp, just you need to find what is yca. Okay. So you want to find yc, that is y. So you need to consider the auxiliary equation. What is the auxiliary equation here? Just put it in terms of d operator. If you put it in terms of d operator, it is simply d square minus 6d plus 9. It is simply d square minus 6d plus 9 into y equal to 0. Into y equal to 0. So that is simply, so therefore your auxiliary equation is d square minus 6 plus 9 equal to 0. The auxiliary equation in this problem with respect to this problem is d square with respect to the differential equation here is d square minus 6 plus 9 equal to 0. What are its roots? So if you want to find out the solution, you need to find the roots of this equation, d square minus 60 plus 9 equal to 0. What are its roots? The roots are nothing but 3 and 3. So d square minus 60 plus 9 is nothing but d minus 3 whole square. It's nothing but d minus 3 whole square. So therefore the roots are nothing but 3 repeated twice. 3 repeated twice means it comes under the category second category. That means if it has got a repeated roots, it has got repeated roots. If the repeated root, the repeated root is 3, and hence your YC is e power 3x, is e power 3x into C1x plus C2 into C1x plus C2. So therefore the correct option here is C1 plus C2x into e power 3x. So therefore option C is correct. That means option C is the general solution of the differential equation d square y by dx square minus 6 dy by dx plus 9y equal to 0. Okay. So such questions will be asked. Notice that. Okay. So let me get back to the slide. Yeah. So we now understood how to find out YCs. So still I need to know how to find out YP. So in general, it's not easy to find out what is YPs. So there are some methods to find out YP when R of X is of some specified form. So in general, it's not easy to find out what is YP. Okay. So there are some methods through which we can find out what is YP only when R of X is of some specified form. So just consider the following cases. Suppose if R of X, that is, if in the differential equation, f of dy equal to R of X, suppose R of X is of the form e power x. Suppose R of X is of the form of e power x, then Yp. So how do we denote Yp? Yp is given by R of X by f of d. Yp is denoted by R of X by f of d. So if R of X is of the form of e power x, then Yp is given by e power x divided by f of a. And the particular integral Yp is given by e power x by f of a. So provided f of a is not equal to 0. And also, if f of a is 0, then Yp is given by x into e power x by f dash of a. So this is also true. This is true where f dash of a is not equal to 0. What is meant by f dash of a? It stands for the derivative of f at x equal to a. It stands for derivative of f at x equal to a. So if R of x is of the form e power x, then Yp is determined as follows. Yp is e power x by f of a for f of a not equal to 0. And if f of a happens to be 0, then Yp is given by x e power x by f dash of a. This is true for f dash of a not equal to 0. Okay. So and also this process you can just continue if f dash of a is equal to 0. If f dash of a is equal to 0. So if f dash of a is 0, then Yp is given by x by e power x by f double dash of a. So now you can see you have a pattern. What happens if f of a is equal to 0, f dash of a is equal to 0, f double dash of a is equal to 0. Right? So the powers of x gets on increasing and the derivative also it could be increased. Right? Power of derivative also it gets increased. Okay? So this is how we find Yp when R of x is of the form e power ax. And if R of x is of the form of sin ax, then Yp is given by sin ax by f of d. That is Yp is given by sin ax by f of minus a square. Actually, this notation f of minus a square is actually confusing. Because actually by f of minus a square, it doesn't mean that you need to replace d by minus a square. Actually, it means that you need to replace your d square by minus a square. Actually, I need to change this notation, but anyhow, I have just cautioned it here. So what is meant by f of minus a square? So if R of x is of the form of sin ax, then Yp it is given by sin ax by f of minus a square for f of minus a square not equal to 0. for f of minus a square not equal to 0, where f of minus a square is obtained by just replacing d square by minus a square, not d. This is the question. Okay. And if suppose if f of minus a square is equal to 0, then yp stands for x sin ax by f dash of minus a square. Then yp stands for x sin ax by f dash of minus a square. Again, the same pattern. Okay. This is true for f dash of minus a square not equal to 0. Again, suppose if f dash of minus a square is 0, again it continues. If yp is given by x square sin ax by f double dash of minus a square. So this process continues until the derivative is from 0. Okay. So similar thing for r of x equal to cos ax. If r of x, if it's of the form of cos ax, then just only the difference between these two statements is that you need to replace your sign by cos. Otherwise, these 2 points they are one and the same. If r of x is cos ax, then yp is just cos ax by f of minus a square for f of minus a square not equal to 0. Again, you have a question here. That is why f of minus a square stands for this obtained by. This just stands for the polynomial obtained by replacing d square by minus a square. Similarly, if f of minus a square is 0, then yp is given by x into cos ax by f dash of minus a square. And this is true for f dash of minus a square not equal to 0. So likewise, we have the third choice also. Suppose if f dash of minus a square is 0, then yp is given by x square cos ax by f double dash of minus a square, or f double dash of minus a square not equal to 0. Again, this continues if r of x is of a polynomial. If r of x is a polynomial in x, if r of x is a polynomial in x, then we determine yp by the method of division. So yp actually stands for r of x by f of d. That is how we denote it. So if r of x is a polynomial, then we try to go for the division method to find out what is yp is. So let me just illustrate this with some examples. Suppose if you have an equation as follows. Suppose you are asked to solve the differential equation d square y by dx square plus dy by dx plus y equal to e power x. So then, you know how to compute what is YC is. So if you want to compute, the first thing you need to know that the solution is divided into 2 parts. One piece is the particular integral, the other is the complementary solution. That is yp and yc. So you know how to find out what is yc is. If you want to know what is yc, just consider the auxiliary equation. What is the auxiliary equation here? It is d square plus d plus 1 equal to 0. So find its roots, right? So depending upon the nature of the roots, whether it is distinct, whether they are same, or whether they are complex conjugates, you can write down yc, which we discussed earlier. So now you need to find out what is yp is. For that, I will look into the r of x. What is r of x here? R of x is e power x. That means r of x is of the form of e power x, where your a is, what is the value of a? Where the value of a is, so it's of the form of e power x with a equal to 1. So therefore, what is your yp? Yp is given by e power x. It is denoted by this e power x by f of d. That is r of x by f of d. That is equal to e power x by d square plus d plus 1. So from the previous study, you can note that the particular integral of yp, if r of x is of the form of e power x, it is just obtained by just replacing d by a. So you just in the denominator, you just replace your d by a. Your a in this case is 1. So if you replace d by a in the denominator, d by 1 in the denominator, it would be simply e power x by 1 plus 1 plus 1. So it is simply e power x by 3. It is simply e power x by 3. Okay. So this is how we need to find what is yp is. So the complete solution, that is general solution, would be yc plus yp. That's the complete solution. So for example, if I consider second one, that is d square minus 4d by equal to e power 2x. D square minus 4 into y equal to e power 2x. Then yp, you know yp we denote it by r of x by f of t. So here I will look into the r of x. Your r of x here is nothing but e power 2x. The r of x is nothing but e power 2x with a equal to 2. With a equal to 2. So therefore just replace your d by 2. So that is the first step we need to do. Here in this case, your yp is e power 2x by d square minus 4. So if you want to determine what's yp, so since r of x is a form of e power x, just replace d by 2. If you replace d by 2 in this case, the denominator term will be 2 square, that is 4, 4 minus 4 is 0. So you are getting f of 2 as 0. If f of 2 as 0, then you need to pay a penalty. That means if f of a is 0, then what you need to do, you need to differentiate the denominator term. So to differentiate this denominator term, you will be getting it as 2 into d. But if you want to differentiate that, then you need to pay a penalty. The penalty is x. So it is simply x into e power 2x by the derivative of d square minus 4. The derivative of d square minus 4 is 2d. So now in this equation, you just replace your d by 2. Okay, again it's of the form of e power 2x by d. This constant term you can just keep it outside. So it is simply x by 2 into e power 2x by d. Again replace d by 2. So it is simply x power 2x by 4. So this is the particular integral, that means the particular solution of this differential equation with constant coefficient. Again, if I consider the next equation, that is d square minus 1 equal to sine 2x, d square minus 1 equal to sine 2x, then yp is nothing but sine 2x by d square minus 1, which is of the form of sine ax with a equal to 2. So therefore, you need to just replace your d square by minus a square. That is, you need to replace your d square by, just I will look into the points that I have mentioned here. If it is of the form of sine ax, then yp is given by sine ax by f of minus a square. What is this f of minus a square? You need to obtain it by just replacing d square by minus a square. Okay. So therefore here, if you replace it by, here your a is 2 here. So you need to replace your d square by minus 2 square, that is minus 4. So if you do that, you will be getting the particular integral as minus sine 2x by minus sine 2x by 5. That is equal to minus, it is sine 2x by minus 5, that is equal to minus sine 2x by 5. Okay, so this slide I have told you about, I consider the example where r of x is a polynomial. R of x is a polynomial. If r of x is a polynomial, then you know yp is denoted by this notation, r of x by f of t, that is r of x in this case is 5x minus 2, f of t is d square minus 1, yp is simply 5x minus 2 by f of t. So if you want to find out what is yp is, then you need to go for the method of division. That is, write down r of x, that is the polynomial, and then divide it by d square minus 1 by writing d square minus 1 in the ascending powers of d. So you need to write down this f of d in terms of descending powers of d. So in terms of ascending powers of d, not descending. Okay. So you just divided this 5x minus 2 by minus 1 plus d square. You need to divide it by ascending powers of d. Okay, d square minus 1 is don't take it as it is, d square minus 1. Put it in terms of ascending powers of d. It is minus 1 plus d square. So divide it as usual. The division process you know how to divide. Just divide it. So if you want 5x, just you need to multiply it by minus 5x. So you'll be fetching this. Subtract it. So you'll be left out with minus 2. And if you want to fetch this minus 2, again you need to multiply it by plus 2. So you'll be getting it as 2. The derivative of 5x, the second order derivative of 5x is 0. So that's why it is 5x plus 0 here. So the final answer will be getting it as minus 5x plus 2. That is, your yp is minus 5x plus 2. So what I mean to say is that if it is a polynomial, Then you need to go for the division method to find out what is copy, and then you can find out the same procedure you can carry out to determine the general solution of higher order differential equation. Also, you can solve third order, fourth order, the same way. Okay. Here I'll just stick on with the second order, but you can just extract, you can just carry out to the third, fourth higher order differential equation also. So these are some other methods. There is the method of variation of parameter, Euler's and Cauchy's second order linear differential equations. I don't think that I will be able to complete because it's already time up. So I just one more to say you that's all the best for your examinations. So, but keep in your mind, so you need to very much thorough with the subject. So if you just read some very standard books, you will get a hold of it, and then you can just easily crack this exam. Okay. So yes, thank you. I think that I have not covered that much of topics, but I wanted to talk about something about linear algebra and differential equations. So I thank everyone for listening to my words. Thank you.
Thank you, Rakshit sir.
Thank you.
Thank you, sir. నేను బ్రహ్మాండ సర్ మెటీరియల్స్ ఇందులో షేర్ ಮಾಡ್ತೀನಿ ಜೊತೆಗೆ నేను